The diameter of the burner is 0.3 meters and the grid density in the flaming region is 6 millimeters. The mass fraction of the composition is for methane 0.16, for carbon monoxide 0.26, carbon dioxide 0.5, water vapor 0.09, and the mass fraction of PPP is adjusted to provide a electrolysis rate of 22.9 kilowatt. In the first, we evaluate the effect of unitrate chemistry considering baseline composition coupled to skeletal mechanism of low wildland. This figure shows the normalized rise temperature and axial velocity along the center line at the burn. The comparison with the correlation of McAfee shows that the model follows the good lines. The fast chemistry assumption can be found sufficient to capture the dynamic of the fire plume. In the continuous flame region, the finite chemistry play an important role by affecting the fine details of the flame, whereas the discrepancies are observed for fast chemistry. So, the use of the fast chemistry assumption leads to over-prediction on temperature. This is attributed to large overestimation in oxygen consumption and therefore attributed to a large overestimation in the local energy released by chemical reaction. Significant discrepancies are also observed for mass fraction of carbon monoxide and carbon dioxide. In the continuous flame type, these discrepancies are of about 15% for mass fraction of carbon monoxide and 14% for mass fraction of carbon dioxide. Now we consider five fast chemistry models. Fast 1 concerns baseline composition. Phase 2 and Phase 3 consider the combustible part in the pyrolysis product as the CO-like fuel. In the Phase 2, the methane are replaced by CO. This leads to an underestimation in the electrolysis rate. Phase 3, the mass fraction of the CO is adjusted to provide approximately the same heat of combustion as the baseline composition. Phase 4 and Phase 5 differ from GPP composition but consider the same heat of combustion as baseline composition. For Phase 4, we consider the composition of Zhou and their collaborators, and Phase 5 consider the composition of Mel and their collaborators. This figure shows the temperature and velocity profiles along the center line at the burner. The underestimation of the electrolysis rate for Phase 2 leads to the discrepancies on both temperature and velocity over fire plume. Phase 3 improves this prediction, however, in the continuous flame rate as well as temperature are always underestimated. Phase 4 and Phase 5 underestimated also temperature and velocity in continuous flame, but a good prediction is observed in intermittent flame region. This figure shows the evolution of mass fraction of oxygen, carbon dioxide, and water vapor. This result shows that an exact number of approximations are able to predict a mass fraction of species. For conclusion, concerning the effect of unitrate chemistry, the result shows that the fast chemistry assumption provide a good prediction in the far future. The temperature and the level of CO, CO2 and oxygen present a significant discrepancies in the continuous flame. Concerning the GPP composition, using a CO which employed always for modeling of the forest fire behavior do not provide a satisfactory agreement with baseline model. The results shows that cellulose give better results. However, it is recommended to use the real composition in the future work if current results are desired. This requires experimental effort to generate a database. Thank you.
Thank you for the presentation. We have time for questions, please, from the audience. Can I ask a question? Yes, of course.
Thank you. I'm a bit concerned about scaling issues here. You obtained your results for 22 kilowatts, which is laboratory scale flame. And here the differences between equilibrium and fast finite rate chemistry can be high, but then you are going to apply your model to forest fires. It's a different scale, it's hundreds of meters and megawatts or gigawatts. Maybe for forest fires such detailed description is not necessary. What's your opinion? Talk too much, yeah?
Yes.
Yeah, okay. In short, is finite rate chemistry essential for very large scale forest? Why?
Sincerely, I don't understand your questions, but can you repeat this?
Yeah. Okay, for forest fires, the time scales are seconds or minutes. It's much longer than your chemical time scales, and maybe infinite chemistry will work.
So, of course, I agree with you. For burner flame, the finite chemistry or fast chemistry is the same. We don't have or different, but the work concerns the difference of the composition. The principal point of the work is to consider the effect of the finite chemistry on the composition. To consider the CO, for example. CO in the fast chemistry is not considered. Her is played an important role in the Fleming region. I don't know.
Okay. Okay. Next question, if there is any question. Okay. Thank you.